Hello, I'd like to welcome you back to part two of this three-part series on a brief side-by-side comparison of Rust versus C++, hosted by the Cybersecurity and Information Systems Information Analysis Center, or CSIAC for short. My name is Corley and I will be the moderator for this podcast. The DoD IACs are sponsored by the Defense Technical Information Center. One of the IAC objectives is to bring industry, academia, and government personnel together to solve hard technical problems. With the support of DTIC, we are able to organize these Code Corner discussions to engage subject matter experts from all professions that are addressing the current and future challenges involved in software engineering and cybersecurity. In part one of this series, we covered the ground rules and the communicator comparison of Rust versus C++. In this segment of the podcast, we will cover the comparison of Rust versus C++ in the following areas: performance, size and complexity, ease of construction, safety, and ease of maintenance. So without further ado, let's get started.
So let's start with the comparisons. So the most important thing to us was performance. So lots of people say Rust is as fast as C++, or no, it's not as fast, or it's faster, or so what. And we wanted to give this a really good, fairly deep view. Now, you got to understand, this is one implementation. So these numbers, are just one point in a random sequence, okay? So it's not, we haven't done 1,000 designs and, average it over that. It's just one. But nevertheless, I think it's gives a pretty good idea of what, how the two languages stack up. So, we're using C++ 17 and Rust 1.48, which are essentially the latest versions. And we're running some tests. These sequences you see here, these are our communication sessions where we have 16 clients, each client sending 1,000 messages. And these are guys who are doing it concurrently at the same time. And we have 8 threads in the thread pool. And the model here is that the machines we're using have 4 cores that are hyper-threaded. So 8 threads probably hits about the sweet spot. We didn't do a whole lot of experimenting with that, the number of possible threads. It's easy to do, but so the thread pools will pull out up to 8 threads. And if a client submits a message and there's no thread available, it just sits in the send queue waiting for a thread to become available to process it.
Gotcha.
And it works the same way on both systems. So, and here you can see in this particular example, the Rust program was transferring 228 megabytes per second. And what we're doing here is we're counting, the way we count that is we count the total number of megabytes in these messages. So 1,000 messages times 4K messages times 16 clients. And then we divide that by the time it takes to send the first message and receive the last message.
Okay.
These guys don't, the senders don't wait for a reply. They send and send and send and send. The connectors have 2 threads. The client has 2 threads, a send thread and a receive thread. And so the send thread just keeps sending, bang, 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 bang. And the receive thread, as soon as something's available, it processes it. So
very good.
Okay. So now here's how this all rolls out. So we have several different environments, 3 different desktops, 2 operating systems, and running on both the native platform and a VMware virtual machine. On Windows 10, so this is an iCore 7 processor. Rust ran 5.2% faster than MPL. And you can see, here's the sequences, here's we took we ran these sessions, each one of these sessions 6 times. So this is this number is like one of these numbers, okay?
Okay.
That was run on a different machine, so the numbers are slightly different. But anyway, so these are 6 different runs, and the average was 215 megabytes per second, and for Rustcom, the average was 227 megabytes.
Very cool.
Now, across these, there's 5 different comparisons. Rust was faster on 2 of them, and C++ was faster on 3 of them. But they're all very close. All, as we'll see, we'll draw some conclusions about it in a minute.
Okay.
So this is MPL on Windows, and this is Rustcom on Windows 10. Here is MPL on Ubuntu and Rustcom on Ubuntu, and here MPL was 10% faster, 9.3% faster than Rustcom on Ubuntu. Ubuntu was significantly faster than Windows in both cases, as you can see, about the same level, same order of magnitude.
Okay.
Here's Rustcom faster on a Xeon workstation. So Mike has this beefy workstation that he uses, and
Yep.
so we ran this on his workstation, and Rustcom came out 17% faster on the native Xeon. MPL was 4.2% faster on Windows Xeon workstation running in a virtual machine. And MPL was 14% faster than Rustcom on Linux. Again, so this is Windows and this is this is Linux, all running in VM. So the interesting thing is that the operating system made a difference in the relative comparisons. Whether we ran on the native platform or in a virtual machine changed the relative numbers a little bit, but not in any major way, not in any way that would worry you if you're in the process of building a server, a production server of some kind. If you want to reproduce the result, you can find the code. These are both links to two different repositories, my repositories for Rustcom and Mike's repositories for MPL. And each of those repositories have README files that tell you how to build them, so you can reproduce the results if you want. So our conclusions were that Rust was, performance for Rust and C++ were very similar and both very good. Size and complexity is an interesting topic, and what I chose to do here, I wanted to keep these measures really simple. This could get complicated in a hurry, and I didn't want that. I wanted to keep the comparisons as simple and understandable as possible. So what I did was I counted the source lines of code. Now, in Rust, I'm counting my use of the TCP stream library. For MPL, I'm counting Mike's use of his MPL plus his MPL library, because we're counting all the code we had to write to do this application. So I thought it was a fair comparison.
Very good.
But keep in mind that that's the way it was. So size-wise, the C++, 5,000 lines of code. For Rust, 2,000 lines of code. And, consider these are relatively complex systems, and it's surprising how nice and compact they are, the source code. It really isn't that much source code,
Wow.
God bless both these languages. That's really good. Number of functions. C++ had more. Quite a few of these functions are in the socket library, and so you would find these much more comparable if we hadn't counted the socket library. And the last way, I like to count complexity, the things that makes testing hard and understanding hard and maintenance hard. are greatly affected by the number of scopes, the number of blocks of code, separate blocks of code you have. And for C++, there were 544 scopes, and for Rust, there were 402. So our conclusions were that Rust is slightly simpler, slightly smaller, but again, not enough to be a decision point if you're building production code. They're both great. Those are really good numbers, really, really good numbers in my opinion. I've written quite a bunch of, a bunch of servers. Mike's written some, and those are good numbers. So I want to talk a little bit about the ease of construction. So, I'm an old-time C++ developer, and I don't have trouble getting stuff to compile with C++. Sometimes when you're writing template metaprogramming code, you might have that can get tricky sometimes. But aside from that niche case, C++ is pretty easy to get make compile. Where you run into problems is debugging. Dangling pointers, especially data races. Data races can be really, really hard to debug. In Rust, because of the guarantees that Rust provides, it's harder to make it compile. We don't have time to talk about the ins and outs of that, why that's so, but there's a bunch of this memory model rules that guarantee safety, some quite simple rules, but not always so simple to use, that guarantee memory and data race safety. But once you get it to compile, you spend much less, I spend much, much less time debugging Rust code than I do C++ code. And that's, bear in mind, I've got about 30 years of experience writing C++ code and a year of experience writing Rust code. So the fact that I debug stuff much more quickly in Rust, that's a major attribute.
Very good.
Really, really good thing. So safety, Rust is, C++ is safe by convention. C++ can be as memory safe as Rust by convention, as long as you follow every single one of the conventions, and they're not, they're not complicated, they're not too hard to use. You can have absolutely safe memory safety. The issue is that when you're writing 100,000 lines of code, it's almost impossible to get every single one of those 100,000 lines of code to obey all the conventions. Even expert developers will slip every now and then. And, if a piece of your code was written by the intern who's in for the summer, it's a whole other story, okay? So this C++ absolutely can generate memory-safe code, modern C++, with all the tools and facilities that are available now, absolutely can. But it's hard to do it in very, very big systems. Where Rust shines is it does it by construction, so there are no slips because the compiler won't let you introduce those slips. And the other major thing is that Rust gives you much, much better protection against data races than C++. C++ has locks and stuff, but it's really easy to misuse and use improperly the locks in C++, and that's not so. Basically, locks in C++ lock critical sections. In Rust, locks lock data, pieces of data. So if you're going to share data, you're guaranteed that everybody's using the same lock. And a classic threading problem in C++ is that you're sharing data, but the two threads are using different locks, and that means they're just not locked. Okay. So, and so these words just summarize all that. Rust is memory safe, guarantees memory safety and data race safety, and none of the other modern languages, they all provide, C#, Java, C++, all provide locks, but they don't provide any guarantees that you're using them correctly. Rust guarantees you're using them correctly. It won't build unless you use them correctly. Okay, Mike, why don't you talk a little bit about maintenance?
Sure, Doc. I think you've got it well organized here for someone to come in and review after the fact. But basically, when you're thinking about maintenance, with C++, you really do have a lot of years of people developing very large systems, and the fact that many large systems exist in C++ are a good testimony to the ability to effectively maintain. I think you have to be careful with C++. Particularly some of the differences, C++ doesn't have a nice ecosystem that's native to it like Rust does with the cargo tool, which helps you to put structure together from the onset. The cargo TOML files let you specify dependencies, and you get a real natural notion of components, or at least the conventions for how you build those pieces and start to layer systems together as they get larger. In C++, there's a variety of different methods, and remember, C++ evolved over a lot of years, so there's a lot of flexibility in there, and I think you really have to know good strategies and good methodologies, and know when to avoid some things too. You can get into a little trouble with the pound include system. C++ uses this idea of includes, and so essentially, when you want to use a library facility, you have to include those library headers, and that's the type information you need for compilation and all. And if you move those headers around, you can really greatly break your build system. You also have a variety of different build systems, and using those effectively is sometimes a learning curve, or potentially a steep learning curve. You also don't have a lot of standard test facilities with the environment. You get a real nice hook that you can establish tests, and you can say cargo test, and the Rust cargo build system will recognize those and let you easily start to facilitate the unit tests or testing for larger reasons. But in the C++ world, not so much. You have a variety of that have been developed, but you kind of have to bolt these things on. And I just think, my personal opinion is, C++ is very powerful. It lets you do all the things that you want to do, but you really kind of have to have a plan and have a sense for the things that can get in your way of being productive. But together, if you know about those things and you put together a strategy that makes sense for your organization and for your goals, I think both C++ and Rust are very effective for maintaining large and complex systems. So that's Dr. Fawcett. Is there anything you want to add to that? Or
yeah, just to reiterate, to emphasize something you said, Mike, Rust has built-in cargo creates. If you want to build a library, for example, cargo creates the file. It sets up the package structure, sets up the directory and the source directory and all that sort of stuff, and creates a file for you. And what's in the file is a little hook for testing.
Yeah.
And so what happens is you'll write a little bit of library code, and immediately you go down and plug in a test. And so it supports us continuously testing you, build as you test, build as you test, build as you test. A really, really nice model for effective development. And the other thing is that Cargo uses a naming convention for its directory structure. If you create a examples directory in the main directory for the package, you name it examples. You can put console applications, and Cargo will link them to your library, and that lets you really easily set up a bunch of demonstrations. Demonstrate different features of the library, or do some testing, that wasn't convenient to do in the unit test in the library, or whatever. So the point is that all of that comes right out of the box with a Cargo tool in Rust. C++, there's lots of test frameworks for C++, and Mike used one of them for building MPL, and but they're, as Mike said, they're bolt-on. They're They don't come out of the box.
Well, that's about all the time we have for this podcast, but stay tuned for part 3, where we'll have the question and answer session related to this comparison. For more detailed podcasts on Rust as well as C++ programming language, please enter the terms CSIAC and Rust into your search engine or browse to our main site at http://www.csiac.org.
Did you know that CSIAC offers free monthly webinars featuring experts in the areas of cybersecurity, software engineering, modeling and simulation, and knowledge management? Come see leading industry professionals talk about industry practices and leading research. Make sure to visit www.csiac.org/webinars in order to subscribe to our mailing list and see when the next webinar series is available. There you can also watch previous webinar series to catch up. Visit www.csiac.org/webinars.